try to take action. And so now what we're going to do is we're going to bring in Spark into the mix. All right, so how many data scientists are in the room? How many people are listening? There's got to be a few data scientists. Okay, how many people aspire to be a data scientist? All right, we've got a couple. Yeah. So the notion of data science is that we're going to be able to, like in machine learning, which is what Spark has a machine learning library. So what we're going to try to do is now make sense out of that data. So in order to use machine learning, we have to have historical data. So what we would do is we would collect that data for drivers over many months. And that's what your insurance company is doing right now if you've got one of those devices. They're not going to hit you up week one and say, you're a dangerous driver, we're going to increase your rates. That would send the wrong signal. So they're going to track your data over many months, maybe a year, before they make a decision. So we're going to collect historical data, and now we want to be more predictive about, we try to build predictive models using some of these tools. All right, and so to show you that, I can switch over once again. So there's one more model here that I can show you. So right now, this screen here is showing events as they occur in real time. So each of these are like happening right now. But what we can do is we can build a predictive model, and we can start to, instead of just analyzing or looking at the raw events like we're doing here, these are raw events. So driver Jamie Angus are just, we know he's out driving on Joplin to Kansas City right now. His last event was a normal event. We're just looking at the real-time data coming in right now. But if we apply some machine learning and we monitor these, we can start to be predictive, and that's what this graph is showing us. Is we're using the same data, but we're using a prediction model to say, based on the historical, we've come up with a model based on historical data. Now, what we want to do is try to predict before they happen. We want to predict those dangerous events before they occur, and that's what this is doing. This graph is being fed by a Spark-built machine learning algorithm, and so it's calling a predict method. And so as these events stream in, in real time we're predicting whether this is going to lead to something bad. So small and green is good, right? Small and green is what we want. This driver, on the other hand, has already had 2 violations. So we need to keep an eye on that. So who knows of some other areas where real-time prediction is in use today? Is anybody here from out of town, or everybody local? Anybody from out of town? Okay. So, for those of us that travel frequently, what do we know about our banks and our credit cards? Frequently, or sometimes, when we go out of town and start charging on that card, we'll get an alert from our bank saying, we think this is a fraudulent card, fraudulent charge. So that's exactly what your bank is doing right now, at least my bank is. Every time you make a transaction on your credit card, that's an event. And that event is going into a system which is now built to predict fraudulent charges. So, it happens to me somewhat frequently. I get a text message from my bank saying, there's a charge of $250 from a vendor you've never purchased before. We're flagging it as fraudulent. We're not going to honor that transaction until you text us back or go online and say that it's okay. So that's happening right now. Now, what's the value of fraudulent analysis or checking for fraudulent charges if, let's say, we go back to batch world, and let's say we just collect all the data, and 30 days after the fact we say, hey, we think this, what is today? December 12th. We think that there was an event on November 12th that was fraudulent. We're going to tell you about that. Well, that's a little too late, right? So you've already paid that. You probably already got your bill for November 12th. So it's an example of, fraudulent, checking for fraudulent charges is not something that's well suited for batch processing. It might be interesting, but it's not going to help the consumer. It's not going to help the bank either. So it really demands real-time processing. It demands that you understand the nature of these things in real time, or at least near real time. So that's what's happening here. So now we're using this prediction. You see now there's a red button here. It says this driver's had we have now predicted, so these are not actual events, we're predicting this driver to have 4 violations by this point in time. And our models that might be because based on this driver's past record, based on the route that he's on, based on the weather at that current point in time, we predict that this driver is going to get in trouble. Maybe he's got 79 hours, it's late, it's raining, bad things are about to happen. So that's when we can really be powerful in terms of having an impact on this, right? So it's important to know historical evidence, but it's way more useful to know in real time what's going on.
Do you call it having pulled over?
Yeah. So so that's when your company has to decide what to do in that situation. So if the so there's a series of factors, and in supervised learning they call them features. So what we've been looking at here for the various features in the feature set, and so in these graphs that I was showing you, so those are the raw events. So the route that a given driver is on, that's a feature. The location, the lat long, is a feature. The certification of the driver, whether that driver has exceeded some threshold of driving a lot of hours driven. So those are all features that we feed into the machine learning model, and then we basically come up with we develop that model and we try to make it predictive if we do our work correctly. So
can I ask you a question? How's that happening under the covers? So I mean, what tools are being used to do the predictive analytics, and then how is it being fed into the system here to keep it?
Okay, good question. All right, so what happens is there's something called operationalizing the model. So if you go up to your team of data scientists, which a lot of companies have now, and you say, well, when they come to work, it's like, well, do those guys? What if this driver is driving at midnight? Well, you don't have any data scientists in the office at midnight. So the fact is that most data scientists do their work on old data. That's where they do their learning. They have to grab historical data from somewhere. So the way that you do supervised learning is you grab a data set, you split it into 2 pieces. You have the training data set, and then you have the test data set or validation. So you use this training data to train the model. And so your model might be logistic regression with stochastic gradient descent, for instance. And so you run through, you develop the model. This is an iterative learning process, training of the data. And then after you develop your model, you run new data or separate data. So this might be 70% of your data, and this might be 30%. So you come out here, the whole point of this is to come up with that model. All right, so now you've decided that you have a model. You don't know if it's any good. So what you do is you run the test data through that model, and then you can evaluate whether it's any good. And so there are standard techniques to evaluating, things. You look at things like the confusion matrix. We can go into that. That's another workshop, which we can do. But basically, you have to assess: is this good? Is this a good model? Yes or no? And if you decide that it is, then you can productionalize that. You can put it into these systems. So now, knowing that you have a highly predictive model, if you're that bank, you're JP Morgan Chase, you can now predict credit card fraud with a certain amount of accuracy, good enough. That might be, everybody can pat themselves on the back, be happy and go home. But until you productionalize that, until you put it into a live system, it has limited value. So what you do is you actually embed, so luckily Storm and Spark are both JVM-built languages. Storm is written in Clojure and Java, and Spark has a Java interface as well as Python and Scala. And so these are all JVM-based languages. So you can develop that model in Spark and plug it into Storm, and that's exactly what's being done here. So we develop it offline, standalone. Once we prove out that it's useful, we productionalize it by embedding that model into Storm, and we call that, and we do something that's called a prediction bolt. Let me see if I can show you the Storm topology live here. So if I want to look at the Storm topology, so we have this truck event processor right now. So this is the Storm UI. You see that, okay, so I just gave you the answer, but you know, Kafka Spout is up there running. There's five executors, 5 tasks. And then all of these bolts are involved. So this is the real system running live right now. So you see how many events, like for instance, have been passed through these in the ACT field right here. So since I launched this topology, there's 73,000 events that have moved through the HBase bolt. The HDFS bolt is right there. So we have this thing called, so HBase is writing to HBase. Okay, so we're writing the dangerous events to HBase. We're writing 100% of the events to HDFS so that we can hook up our analytics, Tableau, whatever, these graphs I was showing you, or Tableau. And so we can hook that up to them. Now, this operationalizing of the prediction is right here, this prediction bolt, right? So that prediction bolt is running here, and that's where we're running these predictions that are generating the prediction graph. Yes?
So, I'm hearing about Spark versus Storm. So why do you need Storm here? You just can't use Spark here?
Yeah, so that's the subject of my talk today. And so let's talk about it. Well, we're about to switch gears. So both of these have streaming processing. So you can do streaming with Storm and streaming with Spark. So why use one or the other? But I think you can, does everybody understand what we're doing? That prediction bolt is running in real time. So we had to go build this model offline on historical data. We had to validate it before we trusted it, but in order to get value out of it, we had to operationalize it, okay? And so that's what's happening right here. All right, so let's shift gears a little bit. So let's talk about when to use. So Storm is not the only game in town for doing this type of processing. All right, so let's talk about the other options. Okay, so Storm, as I told you, was originated at Twitter by Nathan Mars. Taylor Getz is a coworker of mine who is a second most prolific committer to the Storm codebase. So this is a presentation that he put together earlier this year. So I'm gonna use it because it's a pretty good comparison. So yeah, so you hear a lot about, and Spark, as a matter of fact, is probably the most active open source project in many years, if not forever. It now has over 500 committers in the Spark open source. So all of these components are open source modules, and they're managed by the Apache Software Foundation. Every one of them, you can go to storm.apache.org or spark.apache.org. You can go. Not only can you read all about the project and documentation, you can actually download the source. All right, so Spark Streaming came out like a year ago, and everybody wanted to compare it to Storm and say, well, which is better? That's the question everybody asks, right? Before we answer that, let's talk about it in some more detail. All right, so this is Taylor saying that he is a little biased because he's a Storm fan. Okay, so there is so where did Spark come from? So Spark was written by the AMP lab at Berkeley, and so back in 2012 they started to put Spark together. And Spark has a series of modules, the ones I've already told you about, machine learning. There's also Spark SQL, and there's Spark Streaming. So that's one of the primary modules. Is there a question? Question? Okay. All right. So the AMP lab at Berkeley started to put this together, and they created something they call discretized streams. These streams. Okay. So when you're talking Spark Streaming, that's what you're talking about. These streams. So let's figure out what that is. All right. So there was a Spark Streaming paper that was comparing performance And so what Taylor's point is that streaming and batch processing are fundamentally different. So Storm is built from the ground up to be a stream processing framework. Spark, on the other hand, is primarily a batch processing framework, which can also do some streaming, and it does it through what's called microbatch. All right, so when Storm runs, in the topology that we were that I was showing you, it's a tuple at a time. So you're processing a single tuple at a time in Storm. What Spark does is it batches together a series of data points, and then you process that batch at once. So, and Taylor's pointing out here that Storm also has a way of doing microbatching. It's called the Trident API. So Storm can also do microbatching. So, but the difference is pretty easy to explain. So so what happens is, basically over some time window, data is fed in there. So let's use our Twitter example. Okay, so you're listening on Twitter. You maybe you're listening and you're listening for certain events, big data, HTTP, Hadoop, whatever, IoT. You're listening for those events, and we fill out and we listen for some period of time, maybe 2 seconds. And as those events or those tweets come in, they're going to be stored off in this window here into a list. And then all at once, when the 2 seconds is over, or 2 second wait time is over, then this stuff will be sent into Spark, and that'll be a microbatch. Okay, so now Spark will be able to look at all this data at once and process it. So whereas if we were using this in Storm and we weren't using Trident, we'd be feeding one tuple at a time into Storm. Okay, so that's the difference. Now. So batch and streaming, they have some overlap, and that's what he calls the microbatch there. So they can both do this. So this is kind of, I think, what I said. It's belts and bolts, one at a time. And so here's a key point: is when should you, knowing what we know now, when should you use Spark streaming and when should you use Storm streaming? Well, the answer revolves around 2 key things. One is latency, and the other is throughput. So who has a definition of latency that they want to share? Who knows what latency is?
Time to response time.
Time back.
The time, yeah. So, yeah, the time. Latency is the time between the event occurrence and the basically the action that occurs that you take on that event. So a tweet comes in. You take action on it, or in our trucking example, we receive an event that says there's a dangerous event occurring at such and such a place. That's when we receive the event, and then we take some action on that. And so the time lag between this and this, that's the latency. So latency is measured in seconds or milliseconds, something like that. So if you have an application which requires extraordinary low latency, then you probably want to look at Storm. Storm is built for a low latency response system. All right, so now Spark streaming, so latency it's relative. What's low, what's high, what's fast, what's slow. So everyone has their own idea, but if you are in the range, once you get up to let's say 200 to 500 milliseconds, now you're doing something that maybe Spark streaming could do for you. Let's say half a second. So if your latency requirements are half a second or greater, Spark streaming can be used. If on the other hand you need something well below 500, 200, 100, so I can run Storm on my laptop on a VM, and I can get 10 millisecond latencies easily. So if we're down in the 10 millisecond range, then we really want to use Storm. So the other thing is throughput. So first consideration is your latency requirements. Second is your throughput. So obviously we're talking about high throughput. And generally speaking, Storm, you can move more data points through Spark streaming in a given period of time than you can through Storm. And there's actually, I think he has some numbers in here that he talked about. Yep. Okay. So we are. Yeah. So those are the two main things to think about. So you also have maybe things like at most once processing, so guarantees, processing guarantees. So you want to look at those and understand what are the processing guarantees that Storm allows you. Storm and Trident gives you exactly once processing. Storm in either mode, at least once processing. Does that answer your question? All right. So let's see, there's one other demo that I was going to show you. Okay, so
Sorry, one question on that was, does it retain order, or if you have high concurrency, are there any differences in the product?
yeah, so they're both parallelized operations, and so you can. So there are several different levels to think about that. One is at the Kafka level, so as you're ingesting data into Kafka, you generally, for high throughput situations, you're going to have multiple partitions. And these things are going to be in order within a partition, but there's no guarantees that like they're in, that once you combine all the partition data, that it's, so you might have like, T0 go here, T1 here, and T2. And then you wrap it back over here and you have T3, T4. I mean, this is, so you might, is this data in order? Yes, it is. Is this data in order? Yes, it is. Once you collect all this data from the consumers, is it in order? Well, that depends. So you may have to apply some kind of sorting mechanism on the other side, depending on your consumer. So this is at the Kafka level. But Storm can. So even though the topology looks nice and simple out there, you have to remember that anytime there's a bolt, you're really talking about many instances of that bolt. So you write the bolt once, you deploy it many times. So there's many of those. So here's a Spark streaming demo that I can show you on a local cluster. All right, so we have, this data is a little bit different than the driver data. But here we are. I've just run this. Here's my Twitter keys if you want to copy those down. And so what I'm doing is I'm saying I want to connect to Twitter, and it's probably a little too small. Let me see if I can make this kind of bigger. So what I'm showing you here is this is how you do Spark streaming. So what you'll do is you'll use this Twitter utils thing that says create stream. And in this case, what I'm looking for is I'm looking for these terms. Hadoop, Big Data, Spark, Hortonworks, HTTP. So those are the terms that I'm looking for. I use Twitter utils to create that stream. And then this is, there's two times up here. That first one, that streaming context says, I want to collect data for 2 seconds. So that's the micro batch window. So every 2 seconds, I'm going to get a batch of data, however big it is. It might be one tweet, it could be hundreds or thousands, I don't know. So that's where you're telling Twitter, you're telling Spark how often to ship you data. And these are the terms that I'm interested in. And then this thing is, I'm going to create a window of 10 minutes to retain those tweets. So I've already run this here. Now I kicked this off a few right before I started. So at 12:12 at 2000 GMT, I collected these events. So this was, I don't know, an hour ago or something. And next thing I can do is I can create a sentiment. So I'm using Zeppelin here, which is a data science notebook tool. So I'm actually just created a function to generate sentiment from those tweets. And I also want to do a word count. And then the last thing is I want to just start sampling those tweets. So this is about maybe an hour old, but what I'm going to do is I'll be able to see some tweets that were taken from Twitter just, about, I don't know, an hour at 12:12, 2200 GMT. So somebody can figure out when that was. So anyway, I'm sampling this live from Twitter, 45 minutes ago. So those are the tweets that came through. And so here, basically showing you we're doing, we can sample this data using Spark streaming. And then what we can do is we can draw graphs of sentiment. So that sentiment code was grouping things by positive, negative, or neutral. So we'll see that Zeppelin has a graphing capability here. This was the previous run. There were 74 neutral, and so that just changed. It just finished. So I just reran the data on some new tweets, and there's the sentiment analysis. Of course, it can get a lot more involved. We can look for specific words. So I'm using Spark here. This is real Spark code. This is actually Scala, and I'm using the data science notebook to generate this stuff. And what we're going to see is like the words and sort of a frequency of these words. So we're starting to get there's the IoT pound right there. So the point is I'm showing you that these systems can connect to live data streams and do real work. And this is where the data scientists come in, step in, and start to help us. Here's another one we can look at over time. Neutral. We can look at sentiment as a over time series. So as we, and this is what they do in those debates where they have the people monitoring the debates, watching, and they use their little thing to steer positive or negative. They're doing real-time sentiment analysis right there while the debate is live. So we can kind of track that. And these are the tools that you use to do those kind of things. All right, so there's that kind of summarizes the demos. These are really deep and interesting topics. We do 4-hour workshops on each one of these, so hopefully we'll do more, and then we're going to set up to do another one at the next Big Data Conference. Question?
So you guys recently acquired the Onyara team with the NiFi technology.
That's
How
right.
does that integrate into this?
Yeah, that's good. So Onyara was a company that Apache NiFi is another open source project. It was actually developed at the NSA. It was developed over 8 years ago, and it was in production for 6 years. So, what was it analyzing? I don't know. I can guess. Are they call detail records from your calls and mine? Maybe. I don't know. But point is that it's a mature technology because, and unlike a lot of open source projects, it didn't start from zero. It was actually deployed and in use at the NSA. So they spun it out. The NSA spun it out into an open source technology transfer program. It became open source. It became Apache NiFi like a year ago. There was a company formed around that, and we acquired them 4 months ago. So now, and I have another demo that I will show you, but that's basically NiFi. What that does is kind of reaches out to the ragged edge, and that's where these smart devices and the things that we've been talking about, that's where they live. And so NiFi sits out here to gather up. This might be your wristwatch, or it could be some kind of a Raspberry Pi. And so you put a bunch of these edge nodes out here, and they ship data to a NiFi server, and then that consumes all of these messages. And there's full tracking and provenance done on this data. So it's sort of a chain of custody. When you receive a message on this end, you know everything that touched it on the way. So if you have secure data, and you want to know where it came from and when it was generated, you have complete historical knowledge of when it was captured and all the paths, all the points it took to get to where you are. So it's secure, it has provenance. Another thing that's interesting about NiFi is this back pressure. So in a real world system, these are multi-layered. Okay, and so this might be like all the cars on the road, trucks, and this might be some aggregation points, and then this is the server in our data center. So you've got a lot of these things generating events. And what NiFi can do is provide back pressure and buffering. So at all of these connection points, there's the ability to buffer data. Let's say this thing goes offline for 10 minutes. You don't want to lose that data. So NiFi has the ability to store that data right there, and it'll store it and buffer it until this thing comes back online. And then it will start to feed where it left off. So that has the notion of back pressure in a real-time system. It's an important thing to think about in a streaming system like this.
Paul, you can take one more question, then we got to move on.
Okay? Any others? Yes? Yeah, please.
Yeah, so So one of the things that I've been reading so many blogs, why do you need a HTTP if I can do everything with Cassandra and then Spark?
Yeah, well, so we're using a lot of components in this scenario, not just Spark. We're using, if I go back to the architecture slide, we're actually, we're storing this data. So, these are all of the steps in the data. We're enriching with weather data, so we might use Pig scripts to do that. We have that long, right? So we can go to NOAA website or get to their service and start to download the historical weather data. We can always merge that, enrich that data in. So you need other tools to do that. You might need connections to your database, your SQL Server or Oracle database. So you have